Good evening, all of you. Today, it's our pleasure to have Professor Zare, who is with us to deliver the Institute lecture. And before we start with the proceedings, may I request you to keep your mobiles in silent or vibration mode? Thank you. So, brief introduction about Professor Zare. He was born in Cleveland, Ohio, and he graduated from Harvard University with BA degree in chemistry and physics in 1961, and he has completed his PhD in chemical physics in 1964. In 1965, he began an assistant professor at the Massachusetts Institute of Technology, but moved to University of Colorado in 1966, remaining there until 1969. In 1969, he was appointed to a full professorship in the Department of Chemistry at Columbia University, becoming the Higgins Professor of Natural Science in 1975. In 1977, he moved to Stanford University. He was named Chair of the Department of Chemistry at Stanford University in 2005. In 2006, he was named a Howard Hughes Medical Institute Professor. Professor Zare is renowned for his research in the area of laser chemistry, resulting in a greater understanding of chemical reactions at the molecular level. By experimental and theoretical studies, he has made seminal contributions to our knowledge of molecular collision processes and contributed very significantly to solving a variety of problems in chemical analysis. His development of laser-induced fluorescence as a method of studying reaction dynamics has been widely adopted in other laboratories. He has received several honors and awards. To name a few, Professor Zare has received nearly 52 different awards for his research work. Few of them are being mentioned. Kirkwood Medal in 1986, ISCO Award for significant contributions to instrumentation for biochemical separations 1990, Pauling Award in 1993, National Science Board's Distinguished Service Award 1998, Nichols Medal 2004, the Wolf Prize in Chemistry 2005, H. Julian Allen Award, the BBVA Foundation Frontiers of Knowledge Award in 2010, Tobin Bergman Medal in 2012, and the Othmer Gold Medal from the Chemical Heritage Foundation 2017. He has received various teaching awards as well. He has received Stanford University's Dean's Award for Excellence in Teaching, the Big Fellowship Award, Stanford University 1996, Alan Cox Medal for Faculty Excellence Fostering Undergraduate Research, the Lawrence and Naomi Carpenter Hoagland Prize for Excellence in Undergraduate Education, ACS James Flack Norris Award for Outstanding Achievement in the Teaching of Chemistry, the ACS George Pimentel Award in Chemical Education, and the Presidential Award for Excellence in Science, Mathematics, and Engineering Mentoring in 2009.
President Obama.
Again, Professor Zare has received various honorary degrees from various universities, like University of Arizona, Northwestern University, and Columbia University, University of York, and so on. During 92 and 95, Professor Zare chaired the National Research Council's Commission on Physical Sciences, Mathematics, and Applications, and chaired the National Science Board the last 2 years of his 1992-98 service. In 1997 to 2000, Professor Zare served as the chair of the President's National Medal of Science Selection Committee. In 2007, he was appointed to be an advisor to the Camille Henry Dreyfus Foundation and became a member of the Board of Directors in 2010. And most recently, in 2012, Professor Zare was appointed chair of the Committee on Science, Engineering, and Public Policy of the three academies, the National Academy of Sciences, the National Academy of Engineering, and the Institute of Medicine. He also currently acts as chairman of the Board of Directors at annual reviews. Professor Zare has given named lectures at numerous universities and has authored and co-authored over 900 publications and more than 50 patents to his credit, and he has published 4 books as well. So with this brief introduction, now I would request Professor Kankan Bhattacharya to formally welcome Professor Zare to deliver this institute lecture.
Thank you very much. Oh, wow. Look at that. Beautiful.
Thank you.
Thank you.
Thank you.
Yeah. It's very important to know what to do with such an award. What I'm going to do is give this to the department head for his wife. Please accept that.
Yeah. Please join me in welcoming Professor Zare to deliver his institute lecture.
Good. I think perhaps if I go on the stage, it'll be better for you to see me.
The visibility will be good.
Thank you for this introduction. Appreciate it very much. What a wonderful place you have, a paradise, truly. This is my first visit to ICER Bhopal, and I'm deeply impressed by what you have here. I know it's only 11 years, but wow, what you've accomplished. I'm going to be talking to you about microdroplets, small droplets, and really the title of my talk is Water, So Common, So mysterious. Now, why it's common? Sure. About 70% of the earth is covered with water. Rain, we get here much too much right now. We know about water, we think. Or do we? Okay. Water is actually a very strange and odd material. Why is that? Well, this is from the rhyme of the Ancient Mariner, right? In which the person is a sailor stuck at sea, with no wind to blow the sails, and there's all these salt water everywhere, but not a drop to drink, right? Solid ice floats on liquid water. That's the beginning of its strangeness. Most solids are denser than their liquid state. That's not true of water. Why is that? I think it's because the ice has an open crystalline structure. Okay, whereas water, when it's liquid state, snuggles together, and it does something called hydrogen bonding, which is very important. And there's another aspect of water because of this hydrogen bonding that I'm talking about, namely that water has a huge heat capacity, and it takes a lot of energy to raise the temperature of water compared to other liquids. And we all know water boils at 100 degrees centigrade. And for a molecule as small as this, as light as this, we would have thought, well, compare it to something like methanol. It evaporates. That's in water, not the same way at all. And this is very important. Various facts are important here. The fact that ice floats in water means that rivers freeze with ice on the top rather than starting with ice at the bottom. And they don't kill all the life inside the river. The other thing is that water has this property, means that water in our oceans don't boil away, okay, which again would make a very different earth. So very important, these aspects of water. And we're going to see, I'm going to try to show you that that's bulk water, which we think of as what? As being relatively inert, as being quote-unquote a universal solvent. No, it doesn't dissolve everything, but it really dissolves a lot, right? And we think it's pretty good. Oh, yes, if you put sodium in it, you can get something exciting to happen with water, or potassium even more exciting. But by and large, water doesn't, you think, do all that much. Well, I'm going to show you something about water droplets that's very different. So let's begin. Here is my contention, which I hope to convince you. Micron-sized water droplets, microdroplets, that's what I'm calling it, micron size. Remember, a human hair is about 100 microns in diameter to get you calibrated, okay? Show a markedly different chemistry than bulk water. That's what I'm claiming to you. Let's see if you believe me when we finish this lecture. And let's imagine now a conversation I might have with some smart undergraduate chemistry majors. And the conversation might go something like this. I would ask, what's water? And they would say, well, everyone knows that. It's H2O, meaning there's a central oxygen atom and two hydrogen atoms that are bonded to it. Okay? And I would then ask them, well, is that all there is to water? Is there something more to water? And they say, well, if you take a 1 liter beaker, everybody can imagine 1 liter, I hope. I should have brought one, right? 1 liter beaker, and you fill it with water. It contains 55 moles of H2O. And a mole contains Avogadro's number, something like 6 times 10 to the 23 molecules. So it's an astronomical number of water molecules, right, that you find in this. And then I might add, well, in a liter, I'm sorry, I don't know where to stand to stop this feedback. In a liter, is that all you find? Just water? And, well, my smart students say, well, actually, no. Water does ionize to a very small extent. It forms 10 to the minus 7 moles of H plus and 10 to the minus 7 moles of OH minus. The H plus is called, I guess, the hydronium ion, and the OH minus the hydroxide ion. And you see, we take the negative logarithm to the base 10 of the hydrogen ion concentration, and that's why everyone who takes chemistry knows that the pH of neutral water, 25 degrees centigrade, 1 atmosphere pressure, is 7. They smile, okay? And I then say, well, tell me, what do you think is the pH of a water droplet in air at its surface? And at this point, my smart undergrads are a little puzzled because they have never read about this. And they start to think about this. This becomes important. They'll realize that it's probably not 7. Why isn't it not 7? You no longer have this 3-dimensional hydrogen bonding network stabilizing water. So water can more easily auto-ionize, self-ionize. What else? You have hydrophobic air. Air doesn't like to dissolve that much in water. Okay, next to hydrophilic, water loves itself so much, right? And the result of having 2 phases in contact with each other is to develop a very strong electric field. Ask anybody who does biology about membranes, and they'll tell you there's a very strong electric field at membranes. And the same thing's going to happen at the surface of water, of the water droplet. So things are going to be a bit strange at the surface. And I'm going to say more about this as we go on. But we're getting now the feeling that water droplets are not the same as water, particularly at its surface. Do you understand what my contention is? So let's go on. And here's my first assertion to you, namely that reactions in aqueous microdroplets, water droplets, can be dramatically accelerated. The reason they're going to be accelerated is because anytime you have an H plus, you also have an OH minus, and anything which is acid catalyzed or base catalyzed is going to go much faster. And moreover, ions really help to make bonds weaken and go on and make reactions like ion molecule chemistry reactions. Okay, good. Let's see this. And here's an example. This is my postdoc who's responsible for a large body of the work I'm going to tell you about. This is Dr. J.Q. Lee. And here's our apparatus. I come from the background of Dudley Hirschbach involving crossed molecular beams. And I'm going to show you instead crossed beams of water molecules in air in a stream. I speak American, which is different than proper English. So I call these capillaries. To you, they're capillaries, right? These are capillaries. And you squirt water out of these, water droplets, and you do that by having, they're actually double, one cylinder inside the next. There's a little bit of some gas, dry nitrogen, that drives out the droplets. And you can also, if you want, charge them up a little bit externally, and you can ground this thing. That's the mass spectrometer. Incidentally, this costs a great deal of money, and I am indebted to the U.S. Air Force for making it possible for me to have one in my lab. And this we build ourselves, and this doesn't cost anything, much at all. Okay, and it's easy to do, and you can do it too, if you want to. So you need a mass spectrometer for some of the things I'm going to be telling you about. And you all hopefully know how that works. It's a misnomer. It's a mass to charge ratio spectrometer, M over Z, or Z to me. Okay, now let's begin. Let's see if I can make this go. Yeah, come back. What are we going to do? We're going to try to do kinetics. And we're going to look at the kinetics of cytochrome C unfolding. That's a small protein that's unfolding. It's a protein that contains, about 104 amino acids and a heme group. What else do we know about it? It dissolves in water. And we're going to now make it come with acid. The acid is hydrochloric acid, HCl, which we also dissolve in water. And we're going to have these water droplets hit each other, and those that fuse go forward into the mass spectrometer. And the result is we get the denaturation of protein with acid, acid-induced denaturation of protein. The protein unfolds. As it unfolds, it picks up more charge states. More NH2s form NH3 pluses and stuff like that. Most small molecules only have one charge. Put on more charges, they fall apart. But a large molecule like a protein can pick up a lot of charges, okay? And this thing unfolds, and the charge state goes up as it unfolds. This is what is known already about such a system. Let's now go further with this. We've measured what happens to the charge state when we change the pH. Now, this is already in the literature, but this happens to be our data, but it agrees with the same as you find in the literature. When you're at about a little basic, pH 8.5, you see it has 8 charges on it with a distribution. As pH goes to 6.5, a little acidic, right? This starts to move. And if you go to pH 2, look, the peak goes to plus 12. Okay, it's unfolding and picking up more charge. And now let's go further. We're going to set this up. Here's the double cylinders. Here's the gas that fires the things towards each other. Only those that fuse go forward. Those that miss. I don't see them. They're gone. Okay? And the mixing takes place over a well-defined region. And I'm going to measure from this region here to the mass spectrometer. And how am I going to make this measurement? With a ruler. Okay? Now, I don't know about you, but I think I can measure about 1/10 of a millimeter, but no better. Okay? With a ruler. Also, it's very hard to make a factor of 2 error with a ruler. And making a factor of 10 error is just unthinkable with a ruler, right? Agreed? It's going to be important for what I'm telling you. So I really know the distance, approximately, okay? It's going to be poor kinetics, but the first time one's doing kinetics of droplets of this sort. Let's try, okay? And what we do next, I don't know if you saw, I'll try, is we rented a camera. And if I can do this again. And we recorded, we recorded each droplet at 125,000 frames per second. Okay, that's fast. And I had to pay $1,000 a week, so I had the camera only for 1 week. Okay. And then the next 6 weeks or more, Dr. Lee lovingly analyzed each droplet. This is boring. And what is he analyzing them for? He's analyzing them for their speed, how fast they move, and he's analyzing them for how big they are, all of which you can catch on this camera, right? And so now, what did he learn? And, okay, great. What did he learn? He learned that the speed is about 80 meters a second. And moreover, it's pretty constant. We'll only be interested from about 1 to 4 millimeters. And over that range, there's a scatter, but it's pretty constant. Okay? Now, why does it have a constant velocity? Now we go back into physics. Okay? It's the same reason that if you jump out of an airplane, you hit the ground with a constant velocity. That's because of wind resistance, air resistance, right? And in this case, the droplets also experience the same thing. They're being accelerated but they have this resistance, so they slow down. And hitting the ground with constant velocity from jumping from an airplane is lethal unless you are wearing a parachute to slow you down. Okay, but here we go. Droplets are being moved. And now I'm going to do something else. I'm going to, since I've measured the distance and I've also recorded the velocity, it is possible for me to get the time by that amazing equation, distance equals velocity times time. Okay? With me? So let's see what the time is. And the time we're looking at is from about 20 microseconds to about 60 microseconds with these airs on them. Okay? And that's the estimated reaction time in liquid droplets calculated from the measured droplet speeds. And what about the next question? Does the droplet evaporate? Well, sure they evaporate. But do they evaporate in microseconds? Not water. And here they are. Maybe there's some small evaporation, but I'm only going to, again, look from about 1 to 4 millimeters. And over that range, well, there's air bars, but I don't see any evaporation. This is going to be important because lots of people say it's evaporation which causes concentration to go up, and that's why you're going to see faster reactions. And I'm going to tell you, no, that's not the explanation to what I'm going to show you. Though it's an interesting idea, and it may be much truer for organic solvents, not for water. Okay, finally, I think we're ready to ask, do we see kinetics? Well, if we don't, I wouldn't stand here. And we did. Here we go. This is at 0.8 millimeters, and you see it's peaking at around +8. This is 1.5 millimeters. It's beginning to shift. 2.2, it shifted some more. And at 3.2 millimeters, look at that. The peak is around +12. Okay? So we're certainly seeing kinetics. And you can map all this out, and you see that the +8 state's always going down, the +13 state's always going up, and other things that are intermediate go up and down. We're really seeing kinetics. And we got numbers, but the numbers were surprising. And so before I say anything about the unfolding of a protein, which we're measuring, we need to calibrate the system. How are we going to calibrate the system? Here I'm going to take advantage of inorganic chemistry knowledge and spectroscopy. I'm going to use the same procedure used in something called stop flow kinetics. Boy, I look around now and I see we have a full house. That's fantastic. Okay, great, thank you. Anyways, I'm going to use stop flow kinetics. Now, what do? They take ascorbic acid and they take this thing called DCIP. Notice, and you can see what it is. The point is, it's conjugated, right? Alternating single and double bonds, so it's colored. And it forms a redox reaction that makes a leuco compound, which is colorless. And by therefore using your spectrometer, optical spectrometer, they are able to calibrate their system. I'm going to follow exactly the same thing that they do, only my mass spectrometer is blind to color, but it's good to mass. So same technique, okay? And let's do it. Here's the kinetics. You recognize this type of thing, how fast the reactants go away, and it depends on the rate with A and B. This is a general reaction, but there's a trick. If I use 100 micromolar ascorbic acid and 1 micromolar DICP, one's 100 times more than the other, you change the kinetics to what's called pseudo first order. Those of you who remember first order kinetics, it's like radioactive decay. You get an exponential decline with time. And that means if I take the logarithm of the species and plot it against distance, which is the same as against time, I ought to see a straight line, if what I've been telling you is true. And we did that, and here it is with error bars, and we sure enough see a straight line. And we did this from 0.8 to 2.4 millimeters. Okay? And we see this is fine. What more to tell you about this? From the slope, this is sort of reminding you of what you study as an undergraduate maybe in chemistry. From the slope, you're able to determine the rate. And you get out that the measured pseudo first order rate constant is like 1 + plus or minus 0.2, I told you it was bad measurement, not a great measurement, not precise, times 10 to the fifth per second. Okay? And I'm pretty sure it's 1, not 0.5, and not 2. I expect that, and times 10 to the fifth. Now, let's compare it with the literature value, because this has, of course, been done before. And here are the two literature values for the same process. And they get 1 times 10 squared. And they agree within their error bars, you see. Conclusion, our measured rate is about 3 orders of magnitude faster than the rate in bulk. Okay. I was very excited by this result and sent it off for publication. I got back 2 reviews. Interestingly, they both used variations on the same word but reached opposite conclusions. One reviewer says this is unbelievably exciting that you could accelerate chemical reactions by a factor of 1,000. I mean, after all, accelerating by a factor of 2 or 4, you're happy about. But factor of 1,000, wow. Okay? And the other person said, I do stop flow kinetics. This work is unbelievable. I've read this paper several times. I cannot find what's wrong with it. And if it's revised, I don't wish to see it again. That was good because I could get a third reviewer and we got it published. So I'm telling you, it got published now in 2015. And so this next thing are the next 4 years or so of playing with this topic, where it starts. Okay? And I think I'm going to give you some more examples of the acceleration of chemical reactions by droplets. And one of them, you can read the authors, Ryan Bain and Shyam Satyamurthy, okay, was on droplet chemistry, the cycloaddition of diethyl azodecarboxylate and quadricyclane, okay. Another one that hasn't been yet accepted for publication, in fact, just has been rejected recently, and I'll tell you about that, is by people in my laboratory. I have a satellite laboratory at Fudan University. And yet, I think this is clearly a remarkable work. Let's look at it. Here is where it starts. It starts actually with Rideout and Breslow, where they found on-water reaction rate acceleration. They looked at cyclopentadiene and butanone to form these Diels-Alder products, and they found that if they added water, okay, this is not that soluble, and shook the thing, they got big acceleration of the rate. And if they added salt to the water, and so to speak, salted things out, moved them more to the surface, it even goes up some more, a factor 2 for their thing. And then I think this is even more popular by the work done by Barry Sharpless and many co-workers, in which they took this compound, that's the one I want to study, quadricyclane, and this dimethyl azodecarboxylate shown here, and it forms this, okay? Here's what they find. If they do the reaction neat, they have to wait 48 hours at room temperature to get an 85% yield. If they instead add water and shake this, okay, they find in 10 minutes they get the same yield at the same temperature, nearly, okay? So this is exciting. Now, what I thought we'd do is, I think I know why this reaction is happening. I think it's happening because of the droplets. So let's actually make it in droplets that are controlled. And that's what we did. How are we going to do that? We use something that looks like the Greek letter theta. Remember the circle with a line through it? 2 capillaries that bring the reagents together, and only in the air do they form droplets and go further into the mass spectrometer. So I really have, as I say, no dead time, no dead volume in this. There's negligible dead time for mixing. Okay, and here we go, and we've calculated all this, and I'll just give you the results. The result is it's yet 100 times faster than what Sharpless saw by making droplets. Okay, really so, and calibrated all this. You can. I don't want to read this to you. You get a sense of what I'm saying to you. So this is another example, and here's yet another one. And now I've got to get you to understand where this is coming from. Let's go back to our 1-liter beaker. Wish I had brought one. I wasn't smart enough to do that. Okay, 1 liter beaker. If you can imagine a 1 liter beaker, what do you think the surface area is of a 1 liter beaker? Hopefully you'll tell me it's less than 1 square meter. For sure. Right? Hold it in your hand. Suppose I take the water in a 1 liter beaker and I make it into 1 micron droplets, and I use that's the diameter, and I use the formula 4 pi r squared for the surface area. What do you think the surface area turns out to be? And the answer is half of a soccer field, a football field. That's about 3,000 square meters. So if the reactions are happening at the surface or near the surface, I got big acceleration. And it's going to be important to start to understand what's going on. So I think what we're talking about is interfacial chemistry in this process. And I'll try to convince you further of that as we go on. Fortunately, I'm not the only group to have looked at droplet reactions. Other groups, particularly group at Purdue, has also seen marked accelerations in droplets. So let's say that droplets are now well established that you can, for some reactions, accelerate them. Here now is the example of tryptic digestion of proteins. Some of you work on proteins, I hope. Okay? And one of the natural things you do with proteins is you do what's called bottom-up proteomics. You use enzymatic digestion of proteins, okay? And you break down the proteins into smaller polypeptides prior to protein structure elucidation by mass spectrometry. Now let's understand each other. You don't want to break the protein into all its amino acids. That's as useless as trying to find the structure of a molecule by breaking it into all its atoms. You just don't learn anything that way. You need overlapping segments. So turns out the trypsin enzyme cuts arginine and cuts lysine, and so you get fragments that can overlap, and only those. Okay, great. So what do? So in a typical procedure, the protein solution is mixed with a proper amount of some enzyme, such as trypsin, and incubated overnight at 37 degrees centigrade. They pick this because that's the optimum temperature for the enzyme to work. Okay? And come on. To facilitate digestion, protein denaturation is usually performed prior to the digestion to destroy the compact globular structure and expose more proteolytic cleavage sites. So there's more playing around pre-treatment. Okay? Now, what's going to be our approach? We're just going to take an aqueous microdroplet containing protein and trypsin, and here it is. We're going to squirt it. Here's the nitrogen to drive it out. Please notice, no external charge. Just making droplets, like from a perfume bottle. Okay? So you all understand me. And here is the mass spectrometer. And we can vary this distance if we want. Okay? And that'll vary the time, as we've seen. And we're going to what else? We're going to do this at room temperature. Because it's easy. What else are we going to do? We're going to do no sample pretreatment. What can be simpler, right? And now let's pick a system that is known to be hard to digest. Okay? I hope we can. Let's look at myoglobin. Myoglobin has 100-some amino acids, and we're going to look at it. And here's what happens if you use standard electrospray ionization with large droplets. You still have some stuff that's undigested, that's in green, and you get this type of coverage. What about if you do it the right way, which is 14 hours at 37 degrees? You get this much. But look, our method, on the order of a millisecond, the time to fly that distance, is complete coverage. Complete breaking of everything that can be broken. Okay? And I've done this, my group has done this, on now a number of things. For example, Herceptin, which is a therapeutic antibody. We can sequence it this way. Unfortunately, the people who reviewed this say that it may not be the bottleneck in proteomics, and they are not happy with this. And they said, people have already demonstrated you can accelerate chemical reactions in droplets, so what's new? Okay, I think it's quite exciting, because I'm going to try to say again, it is the first example I know of accelerating enzymatic reactions. I don't know of another. Okay? We'll go on. Here's assertion 2. Reactions in aqueous microdroplets can yield different products than the same reaction in bulk water. Okay? Well, if you start to now think about it, it's going to be interfacial chemistry, and I'm going to have H plus and OH minus around to help me. You might not be surprised. But let's see if this is so. And so my next assertion, the surface of aqueous microdroplets are both more acidic and more basic than bulk water. Well, I've told you why. Kw, which was 1 times 10 to the minus 14 in bulk water at room temperature, may have been changed to something like 1 times 10 to the minus 6. 8 orders of magnitude. Huge change. Still isn't many ions, but I mean, this is a lot. Big change now. And there's evidence to back up that type of estimate, which I can go through in questions and answers. Aqueous microdroplets give rise to redox chemistry not observed in bulk water. I want to prove that to you. Okay? Redox involves reduction oxidation. Let's all remind ourselves. Reduction, okay, is the gain of electrons, and oxidation is the loss of electrons. Okay? And the smaller the microdroplet, the larger the effect over the range we've studied. You'll really see this. So, next thing I want to show you is thermodynamic changes in microdroplets. Here's an example. This is something called a sugar called ribose. Okay? This is phosphoric acid. You can dump these two together in bulk water and nothing happens. Okay? I'm going to show you that if you make little droplets, you get ribose phosphate. And ribose phosphate is pretty exciting for those of you who know biochemistry. Okay? Is starting to be, and we've done a whole bunch of sugars can be phosphorylated in droplets. Please notice, no catalyst. Okay? No charging, just droplets. And I'm showing you the result of that. And you can pick out the data and it goes. Okay, let's go on. In bulk, the free energy change is positive. Positive 5.4 kcals per mole. It won't go thermodynamically. What happens in the droplet? Well, we've played it and we see it goes. And we've now studied it as a function of temperature. And we make what's called the Van 't Hoff plot, of plotting the equilibrium constant of this versus 1 over the temperature, for which we're able to get out what the delta S is. We find that the delta S is very small in the droplet, that somehow the surface becomes stiff, becomes viscous. Well, we're going to see why. With all these charges, in fact, I should go further and tell you more about the charges, okay? Because I don't want to make this a mystery. You have H plus and OH minus. Which one loves air more? Which one loves water more? Turns out H plus likes the water more, and OH minus likes to stick its O end into the air. Okay, and calculations show this. Now, if you separate OH minus and H plus just by an angstrom or two, what do you have if you pull two charges apart? Back to physics. Big electric field. That's where your electric field's coming from. Okay? And that electric field is going to propagate. And you're going to see the effect not just at the very periphery, but it's going to go in a little bit. And you expect this to happen. And with such a large electric field, it's going to become rigid. Things are going to become aligned. They're not going to move around much. Okay? And, okay, so now let's go on. Molecular localization and alignment at or near the microdroplet surface. And I'm going to show you that using confocal microscopy, right? We can go and we can look at these various molecules, and the molecules are localized and aligned at or near the surface of the microdroplets. This is work of my graduate student, Chen-Pong Zhou, who's now got his PhD, and he put in rhodamine and used polarized light. He used polarized light to excite, and he looked at the fluorescence. And you can see it's all with another cross polarizer. And you can see the molecules are standing up perpendicular to the surface, very rigid. And they're being held there by this strong electric field. And it propagates a distance in. It's not just, after all, you know, I'm seeing it going on for a couple microns, and that's large. Consider the size of a molecule, nanometers, okay? So it really is going in for a bit. And this probably means there's also a pH gradient and an OH minus gradient, H plus gradient, okay, no OH minus. What else? We can measure lifetimes. This molecule, when put in the excited state, can rotate and go into a dark state. It's called Psi3. This one is locked, can't move. Sure enough, this one shows no effect wherever it is. This one, however, really shows a difference, that the lifetime is much longer at the surface, at the periphery. That electric field is really holding it, letting it not rotate so fast. So there's real, unpublished again. Sorry, lots of unpublished work here. And I think this is pretty interesting to see this type of phenomena. So a picture's really beginning to emerge. Let's go further. Now comes this experiment. For fun, anybody, just show you, anybody make a gold or silver film? No one in the audience at all? No one wants to admit to making gold or silver? A couple people, okay. And this is common. In fact, if you look back at the history, in the Middle Ages, in Europe anyways, people doped glass to make it red for cathedrals with colloidal gold. The first person who knew what they were doing was a great physicist and great chemist by the name of Michael Faraday. And what Faraday did is he took this material called chloroauric acid, HAuCl4, and he put it in water. That makes H plus and HAuCl4 minus. Okay? And then he added a reducing agent, something which adds electrons. You see, formally, the gold in HAuCl4 minus is +3 with -1 for the 4 chlorines. Agreed? And this makes now gold 0. And he did it with lemon juice. I mean with citric acid. We're going to do it the modern way with sodium borohydride. And I said to my group, you know, if we can accelerate reactions, why don't we try this one? This one looks so interesting. And let's go do this one. Because people also were giving us a hard time. They said to me, what you're doing must involve a mass spectrometer artifact. Because I'm using such a mass spectrometer. And now I want to do something with no mass spectrometer. And here's what we do. We just use a glass slide and collect what hits it. No mass spectrometer. I'm sorry to also tell you, no laser. You haven't heard of laser this much at all. Okay, anyways, continuing. Here it is. We can vary the distance, and we can see this work. And we did get it published in 2018. And we got a factor of 10 to the 5th acceleration. But at this point, you're familiar with this. In fact, my postdoc, Shibdas Banerjee, showed more than a 10 to the 6th acceleration in making isoquinoline by using droplets. So, okay, these are big things that are happening. Okay, and now I said to the group, you know, we ought to do a control experiment. And what we should do is remove the reducing agent. And I knew that nothing would happen, because you put chloroauric acid in water, just nothing happens. Okay? So how do we do that? We just replace this with pure water. And here we are. And we put the microscope slide in, and we saw gold nanoparticles. I immediately said, this is contamination. They said, no, it's not, because we've been very careful, and we repeated it, and we convinced ourselves that it really is so, and it changes with distance, and it does all the right things. And then we submitted it for publication. That publication was delayed about a year because no one wanted to believe this, and part of it is they kept asking, where are the electrons coming from? Right? Where are the electrons coming from in this process? And this will return as a theme. Okay? And now I want to tell you about the reducing agent-free synthesis of gold nanoparticles and microdroplets. I think I just showed you that. And you can just see you get wires, gold nanowires, as well as nanoparticles. Incidentally, they're catalytically active. There's much more to be said. And you can do this for other things. And I believe it's the strong electric field which helps it grow. The electric field is estimated, here's a publication in 2018, theory only, that it's 1.5 gigavolts per meter. Okay. And now, in a collaboration with Professor Wei Min at Columbia University, and J.Q. Lee went there to work with them, we wanted to actually, for the first time, measure the electric field. The work I'm again showing you is not published. Okay? And here's how we do it. We use this compound with a CN group, which makes very sharp Raman lines. And we use a technique in which you have the Raman, that's a weak process, followed by fluorescence. And by putting the two together, you really can see it quite well. And we find a shift, bulk water versus the particles, the droplets, of 5 wave numbers. That's a Stark shift. And that Stark shift turns out to be on the order of about 10 million volts per centimeter. Huge electric field. You can't generate an electric field like that in the lab. Between capacitor plates, you get lightning. Okay, you get breakdown. Okay, but you have, of course, you have that. And that's being set up here. So I really am convinced about this field. This is going to be important, what I'm telling you, because I think that field actually helps the OH minus molecule lose its electron. If you think about it, okay? Makes it weaker. Let's go on. I want to now tell you about micron-sized water droplets induce spontaneous redox reactions. Here's the setup again. We use a silica capillary. We've also used stainless steel that's been grounded. It doesn't matter what material we use. It's not the material. Because some people are going to say, oh, this is triboelectricity, just rubbing against this material, why it gets charged. No, that's not what's important. Here's the nebulizing gas. We've played with the nebulizing gas. We've used pure oxygen, pure nitrogen, and pure argon to get a sense of what's happening. I can talk about that. It's not caused by the nebulizing gas. Microdroplets into our mass spectrometer vary the reaction distance, and what do we see? I'll give you an example. This is the molecule called pyruvate. We all have pyruvate in us. Pyruvate is one of the last steps in the Krebs cycle, okay? And the conversion of pyruvate to lactate is enzymatically catalyzed by this thing called lactate dehydrogenase. And in this reduction, pyruvate gains 2 electrons, becomes reduced, and is converted to lactate. And this thing loses 2 electrons. It goes from NADH to NAD+. And lactate dehydrogenase converts pyruvate, the final product of glycolysis, to lactate when oxygen is absent or in short supply in muscle cells. That's why you ache if you exercise too much. So lactate, okay? Lactic acid buildup. Fine. If you put pyruvic acid in the water, bulk water, you got pyruvic acid, nothing happens. Now, we're going to spray droplets. And we see lactate, okay, without question. Incidentally, you might say, again, you know, if this is true, you ought to collect your droplets and do NMR. And we have. And what I'm telling you is also supported. This is really happening, okay? And we've done this for a whole bunch of organic compounds that we can see reductions that are going on. And I've now given you an idea of where the reduction might start to come from. Let's go on further. Oh, I'm showing you as a function of distance. You can watch it grow. You can calibrate the system. Math is never any fun to present in a lecture. Just trust me. We worked out the reduction efficiency for different intensity, concentration, and ionization efficiency. And we get that if you have a small amount of pyruvate, you're around 90% converting it. Okay? If you make a lot, well, you can only get so much to the surface. Incidentally, as I'll point out to you, the smaller the droplet, the more diffusion back to the surface, the easier it is to make all this work. Okay, another example. This is a compound called hazarin, okay? And when it's reduced, it becomes fluorescent. Look. See? Confocal microscope with droplets. Look at the ring. We see it. Here's bright field, and we see it's happening and localized at the surface. If you believe so far what I'm saying, then you must conclude that there is an OH molecule around. OH molecule is called a hydroxyl radical. It's highly reactive. It's what's used to clean up our atmosphere. And atmospheric chemistry is a big deal. Okay, and well, we should be able to catch it. And to catch it, we added salicylic acid, and we formed these compounds, which have the same mass, okay, but different configurations. And sure enough, we see it. So we see that there is OH. Okay, now we've really shown you that there's OH in our droplet. And now this is what I'm next going to tell you. If you got OH radicals that are running around in water, they're going to find each other, particularly when there's lots of them at the surface. When OH radical comes and bumps into another OH radical, they recombine. And what do they form? They form H2O2. That's called hydrogen peroxide. So if this is true, we ought to be able to see hydrogen peroxide being formed. And to test that, my student who's now gotten her PhD, Catherine Walker, made this compound. It was first made by people at Berkeley. Anyways, this is broken apart by hydrogen peroxide, and look what it leads to, fluorescein. Well, that's a nice molecule. That's why it's been made, so we'll be able to see it. Now, look at it, please. I need a name for this, and I don't want the chemical name. I'm going to call it PF1, okay? And let's add PF1 in bulk water. Here's the fluorescence spectrum. Here's bright field. I see nothing. Here is air-water interface. I still see nothing. Okay? Now, here are droplets. Look, here's even the air-water again. Don't see it, but I see the droplets. They light up. Okay? Wow, I got hydrogen peroxide, I think, right? Well, let's study it as a function of droplet size. And sure enough, here's a droplet that's 160 microns in diameter. This one is 50 microns in diameter, and this one is 16 microns in diameter. Only those, if we could kill all these lights in front, you'd see it. Only those in the front could see there's a little green here, almost nothing. Okay, this is clear there's some green. This stands out. The small droplet, this thing just takes off. And we really get lots more hydrogen peroxide being formed. So we're seeing that small droplets really matter in this. Okay, let's now show it another way. This is a peroxide test strip. I should explain that. One takes the enzyme horseradish peroxidase, and one takes a dye that will be activated. This dye is going to turn blue if there's hydrogen peroxide. You can take these test strips and dip it in water, nothing happens. Now let me spray. I need to show you this. I'm sorry, I wish the lights here could be killed, but I can't. Okay, this is right here's the little capillary making the droplets come out. This is the air. There is no electric field being applied. Thank you so much for bringing the lights down. And now, if I can run my computer's video, I'll try to show you what happens. Let's try. Oh, that's good. Okay, this is good. And if you look carefully, you can see it's wet here. That's the water coming out, little droplets. Now slide this over. Come on, you can do it. Slide it over. There we go. And that's a little test strip. And now we're going to play times 10 because otherwise it's like watching paint dry. And I claim, if you look hard, that this thing will change color. Okay, do you see anything? Well, I do. And I think I really do. Okay, so it's pretty clear. There's hydrogen peroxide. Okay, let's now go on. And what I'm going to do next is, unfortunately now another unhappy story. J.Q. Lee wants to go to Korea. He says the only way you can get a job in Korea is to publish in Nature. So we submitted this to Nature, and we got back all types of statements, we did get some people to send it out for review, but the reviews would come in mixed. And they would come in, people said this is fantastic, and other one says that it really is fantasy, can't be true. It really was that way, okay? And the Nature editor is averse. See, if you'd been an improvement in a battery, that would have gone through pretty easily, but it's not. This is something altogether different, and so not happy, very nervous about this. Statements were made to me by the Nature editor. I'm quoting, what's her name? Okay, Magdalena Helmer. She writes to me, Dick, people call me Dick. Dick, she says, people have been studying aerosols for years. If this were true, it would have been seen already. This is a very hard argument to fight against. Because this type of argument means nothing new can ever happen. Okay, but I'm going to show you. Here's rain droplets. And sure enough, in the nighttime, people have measured there's hydrogen peroxide in the rain. People have written, oh, this all comes from ozone being photolyzed. Well, maybe, but I think it just comes from water droplets. We have unpublished data in which we've just poured water to make droplets, and we see hydrogen peroxide in the small droplets. I'm going to show you more, if I might. Another video. Hope I can run this. Okay, come on. Yeah. Right? You're used to waterfalls, I think. And this man, by the name of Leonard, a great physicist and horrible human being, okay, but an excellent Nazi. Okay, anyways, he in 1892 found that there were negative charges that tend to appear in the air and positive charges tend to stay in the liquid, is what he's saying about waterfalls. This is called a waterfall effect. And then more recently, okay, come on. Maybe I click this. Click this. Okay. More recently, 2006, these people in Finland and Estonia, okay, published in atmospheric chemistry and physics discussions that in this study we measured to our knowledge for the first time the mobility distributions of clusters and intermediate ions with an ion spectrometer near a waterfall. We observed that the concentration of negative ions was 100-fold compared to a reference point 100 meters away from the waterfall. Also, the concentration of positive was found to be higher by a factor of 10. The increased concentration of negative intermediate ions is assumed to be due to the so-called Waterfall Effect. They attempted to explain it using Kw equal 1 times 10 to minus 14, and they failed. Okay? But we now are, all of us, gotten smarter. We think it's very likely that you have this charge separation at the surface. I've been telling you that. And then in fragmenting, I think it's quite likely to pick up charge separation. Okay? And certainly that's what's being seen. I have another speculation, again, unpublished. I think this is going to be responsible for why there's lightning in clouds. Okay, what sets it off? And I think it comes from some of this. Again, someone else will tell me no and give me a better understanding. But I think this is very interesting. This stuff, which all starts out being little droplets of water in which people say, water is water, what is there to learn, is turning out to be quite amazing to me. But go on. Water droplets are everywhere. Okay? This is going to be interesting because water droplets are about the same size as cells. They're like protocells. And the fact that you can see reductions and oxidations in water droplets without enzymes may be a hint how you can go from non-life to life. So this becomes interesting another way. We'll go on. We can do something else with it. And we're just now more unpublished work. Collaborating with Denise Monak, who's a professor in the medical school in virology, we've been looking at bacteria. And we find we can kill the bacteria by spraying water droplets. Little water droplets. That's nice because that's pretty what you call green or environmentally friendly. And we're very interested in seeing if we can develop this into a disinfectant. I'll go on to the next part of the story. I think time is running out on me. Okay, this is Fong Jin, who is involved in a drug company, but the leader of this project is Dan Gao. And she's an associate professor at Tsinghua University in Shenzhen. And this is close to my house on the beach in Aptos, California. Okay, and this is going to be an application to organic synthesis. We're going to look at something called the Dakin reaction. Okay, Professor Roderick Braitz knows more about this than me, I'm happy he's here. Anyways, this type of thing turns into this, okay? And I'm going to talk to you about something called the Baeyer-Villiger reaction, in which you can stick an O atom between CC bonds when you have a carbonyl. And that's the type of thing you're trying to do. And I'm going to show you that with no oxidant and no catalyst, okay, in aqueous microdroplets, you can make this happen. Here's again the same setup. You're now used to it, okay? And here's the example. First, hydrogen ion sets this up. And we got that at the droplet, as I told you. Then HOOH attacks it. We also got that in the droplet. And look, this thing goes on. You can follow it through. And you end up with this. Well, we've looked at this, and we see these, okay? While we don't see them in great yield. The yields vary from, about 3% to 25%. So once again, this work has been recently rejected because it was said that the yield's so small that no one cares. On the other hand, I think it's pretty neat. I'm sorry, I'm here with all my bruises from battles, but I'm trying to show you what it's like. But I think it's pretty exciting to see this type of chemistry can be done so simply. And it's a question of can we later on learn how to do this and make this run at a better rate. And I'm showing you another reaction. Oh, I'm showing you scale up of microdroplet reactions by heated ultrasonic nebulization. And here's what we're doing. This is the scale up of reactions was achieved at an isolated rate of 19 milligrams per minute for the product of the Claisen-Schmidt condensation shown here, at 21 milligrams per minute for the synthesis of benzophenone oxime from benzophenone, that's this thing, and at 31 milligrams per minute for the synthesis of this compound from this, as you can see from here. Okay? This is neat, okay? I think it's neat. And we do that by just shaking it and making droplets and running it like so. No electric field again, just water and dissolving the material. And now this, I think, might be interesting for the pharmaceutical industry, but we're never going to put this into a boxcar at this rate. Now, if we want to go further, what we have to learn to do is to make fog, big mists, okay? And now there may be ways to do it. Now I'm looking for help from chemical engineers to help me try to get to that stage. So you know what I'm trying to do. And so here's what I'm claiming to you. Now, I hope now you sense what I'm trying to say. Water microdroplets, less than about 30 microns in diameter, behave very differently than bulk water and open a whole new area of research I call microdroplet chemistry. And that's why I love microdroplets. Thank you all.
You all will agree with me that it was a fantastic lecture by Professor Zare. Thank you. So we will be having time to have 2 quick questions from the students first.
Hello. That was a great lecture, sir. So one question, like in most of the experiments, you made droplets of both the chemicals, like water and what it was reacting with. So is it possible that if we just spray water droplets on a surface and the reaction would still happen?
Yes, and that's what I was trying to show you at the end. Just pure water can act as a disinfectant when made into small water droplets and then react with the surface. Yes. Otherwise, I mix the chemical with the water. The chemical doesn't react in bulk water, but in the water droplet does react. Before I was taking 2 beams. I don't need that anymore. Once I discovered that it's just the droplet itself. And I hope you understand that this experiment came about basically as accident. It's not planned. Okay? you could present this talk as if how smart we were about doing this. It's not true. Sorry. It was a matter of following up things that we didn't expect.
Okay, another question, like, so what is special about water here? Like, if we...
It's what's special about water is that it ionizes to a small extent. And so if I try the same thing with methanol, and I have, I find I have to actually charge the methanol a little, whether it's positive charge or negative charge, to start to make things happen. I need charge. But methanol itself doesn't ionize as well as water. And I don't need many ions. Please, I didn't say it, but please notice, if you use up the hydrogen peroxide at the surface, guess what? It regenerates. It's an equilibrium process that's going on. Okay? Or steady state process, whatever we want to call it.
One more.
Yeah. Okay.
Thank you for the amazing lecture, sir. I could not understand the entropy argument that you made that made the surface of the water droplet thick. I understood the electric field argument that the electric field could rip off the electrons and help in reduction. But entropy, you said entropy was low and that helped in the...
The delta S for this process appeared to be very small compared to what it is in bulk water. So in bulk water, things seem to be able to move away and mix. And here at the surface, over the time scale of the reaction, they seem to be held very strongly. That is again related to the electric field and to the alignment of things in the electric field. So it seems. All I can do is tell you the measurement, and I did measure delta S, or the group did, right? And that's what I'm seeing. Is that? And incidentally, I hope you all know, there's so much to do in this area. Droplets belong to no one. You can use them yourself, any of you. No, I mean, this is important to understand. There's nothing stops you from doing this work. There's so much more to do. Okay, I wish people would try to play with this. There's, I think, a lot of fun here. It really says that interfacial chemistry is a new big area to me. Anyways,
yeah.
Thanks.
Thank you, sir.
One more, please.
So, yeah, I just noticed that you did not use any vacuum when you nebulized this thing.
Well, there's a vacuum in the mass spectrometer, but otherwise it's in the air.
So doesn't it damage your spectrometer?
No, because the droplet goes to a heated inlet into the, and people do this, can put droplets into mass spectrometers and it works.
Okay, you don't get a background noise
it's okay. It really does work.
Okay, because usually you would use a very high vacuum to transfer.
Well, it ultimately is a high vacuum because you have to that way.
Okay.
Okay.
And another question regarding the synthetic utility of this process. How much is the percentage conversion that happens here?
For the particular Bayer-Villiger type reactions I was showing you, the conversion efficiency is somewhere on the order of 10 to 20%, which is poor. Okay, that's poor. So you understand me.
Yes.
And but maybe first of all, if we could recycle the droplets,
yes,
it might be fine. We haven't done that yet. Just for fun, so you all understand, who's supporting this work? I have only one sponsor, the U.S. Air Force, for the mass spectrometer, okay? Which I have to keep pleased with this. And
I was just wondering whether you could, use it in a gas flow reactor.
I don't know. But I can also tell you something else. This effect works also on films, but less because there's less surface area. It also works if you put your droplets into oil. You don't need water. In air, okay? So I need hydrophilic, hydrophobic in contact with each other.
Thank you.
Okay.
Ashish.
Reviewer type question. Is it also happening due to the shear forces that are happening when you are making nebulization?
Well, I wondered about that. And so we've varied the rate of flow and things of this sort. And it appears that it is not rubbing that's causing the charging of the system. Okay.
Ankur, this is the last one.
But maybe I'm wrong, but that's what it looks to me.
So this is about the Stark effect, actually. So when you're talking about this, actually that got lost somewhere about the cytochrome C
yes.
Unfolding experiment. When you're talking about these large electric fields, the proteins are sensitive to those. So Professor Moorner at Stanford uses a microfluidics setup where, again, he develops these very large electric fields. And there he says, well, it does not hurt the protein. Now, what you're saying is you are looking at this denaturation of the protein, and that's simply because of the pH.
Well, I added acid. That's right. I added HCl.
So, but the large electric the field gradients.
The field itself is not what's hurt. That itself alone on a protein won't do much. Okay.
But why not? I mean, because the protein itself is a charged moiety.
Well, okay, it may at the surface a little, but by and large, I don't think that. I don't know. I don't think that's what's happening. I haven't done it just in a. Well, I did in the sense I've just put it in a droplet itself, and it doesn't do much. I need to add acid to the droplet to make the denaturization happen.
Okay.
That I saw.
Thank you.
Okay.
And
yes.
one more thing, follow up. So when you're saying that you're using just the water spray on top of your petri dish, where do you think you're making hydrogen peroxide? While it's in the droplets, or when it attaches, when it reaches?
No, I think it's being made in the droplet.
But then where are the electrons going?
From OH minus.
Where are they going? So you're getting
the electrons are going into water itself to make, like, for example, hydrated water, I think. But are they going somewhere else? Maybe they're going into air. I don't know where they're fully going. Okay, so you understand. I don't have that part well established yet.
Thank you.
Fair enough.
Yeah.
But what I'm telling you is really so. It really is acting this way. But I don't fully understand it all. Incidentally, I'd love for somebody to do modeling. No one yet is brave enough to do modeling. When I ask people, the theorists in my group, at Stanford, why don't you model this? They say, look, you take water, and water hardly ionizes. You know, KW's 1 times 10 to the minus 14. We can hold 1,000 molecules. Nothing's going to happen. You put 1,000 molecules in, then there's nothing going to. Well, so you have to add ions, and they don't want to do it so far. I hope they'll change their mind. Maybe some of you here are interested in that. Yeah. I need help to understand this further, okay, as to what's happening.
So due to time constraint, we are winding up at this point. And please join me in thanking Professor Zare for the fantastic lecture. I hope you all enjoyed. So now I request Dr. Srivastava to come to the stage and hand over the memento to the speaker.
Oh, wow.
It's a sculpture model. Thank you, Ashish. Thank you. Thank you. Thank you all.
But it's an interesting thing.